Hello, my name is Johnny, and I am your CCNA instructor for this CCNA video series. And in this video, we are going to go over QoS classification and marking. Whew. So, you see this up here? The CCNA symbol? This is a CCNA instruction, meaning we are not going to deep dive like a lot of the people out there on the internet maybe want for QoS classification and marking. We're going to go over this at a high-level overview. I'm going to show you IP precedents, or show you classification and marking at layer 2 and layer 3, how they differ, and then the differences in the layer 3 markings. And that's it. I know this can be pretty complex. We can get into the binary and spend 2 to 3 hours on this. But again, we're teaching for the CCNA. So my job to you is to teach you the per forwarding hop behavior classification and marking. So with that being said, before we can apply any traffic shaping, policing, or queuing, we have to mark and classify our traffic. So we need to put our traffic into different groups and mark the priorities of packets. So these classification groups, right, or these classes, you're going to learn these are called class maps. They can be very broad or very specific. So we can make a whole class of traffic just for VoIP, just for email protocols like POP3, IMAP. We can do a whole classification just for IM. But Cisco best practice says that you shouldn't have more than 11 classes that you're either queuing or shaping or policing on your WAN edge device. So, and on your layer 2 and in the enterprise, right? If you're layer 2 doing layer 2 markings, you shouldn't have more than 11 of these groupings or classifications. And then markings. So we're going to mark IP traffic that belongs to a certain classification. So I'm going to teach you how to do that. So we can either mark IP packets using like a type of service or a QoS byte. This is be our layer 2 byte, our layer 3 byte. Or we can classify it based off just protocols. Or maybe we want to implement QoS and we don't want to put an IP precedence or a layer 2 class of service marking on it in the actual header. Maybe we just want to classify based off protocol. So when it goes to queue or police on our router, we just look at, oh, this is email, so we need to queue it and police it this way. Or we could also mark it with these, in these TOS or COS bytes, or fields rather, in our layer 2, layer 3 headers, and then we can queue and police and shape based off that marking, which we can also put these markings into a classification group. So it can get pretty complex. So that's why I want to take some time to go over these classification and markings. And then the per hop forwarding behavior. So that kind of goes into our trust boundaries, right? If this is an ISP and we don't have that label switching end to end, we're just sending off this broadband connection and we have a hub that we like to reach. If we don't put some sort of tunneling mechanism and then configure QoS to actually work in this tunneling mechanism, then we're not going to have that per hop forwarding behavior. So essentially, let's say this router connects to this router, but there's 6 routers in between. If these routers aren't agreeing on these markings, or they have a different policing policy, they have the ability to remark this traffic. So if you sent HTTP with an AF bit of 32, which we'll get into, this router, let's say R6 here, can change that to AF11. So the per hop forwarding behavior is that it can change at each router, or you can have this router agree to those classifications and QoS markings. And in the enterprise, that's where you come in as a network administrator. From that hub to spoke topology, you want to agree on the QoS and the quality of service you give the users enterprise-wide. Okay, so marking at layer 2. We call this the class of service bit. And this is going to reside in your encapsulation header. So we know about 802.1q. That's how we do logical segmentation of our layer 2 traffic. That's our VLAN tag. Well, in the actual VLAN tag, that 802.1q header, it's a 4-byte header. In there, we have the VLAN ID. That's going to have 12 bits. And then the rest, right, because 16 bits, so in this 4-byte header, we have 2 bytes. This VLAN ID is part of those 2 bytes, but it's only 12 bits, so that only takes up 12 out of 16 available bits in a 2-byte header, right? Kind of doing some math there. Well, there's 3 bits called the priority field within those 2 bytes that is going to be used for the class of service. So those 3 bits, if we put like our chart up there, right, of the bit values, those 3 bits, depending on what they equal to, is going to give them a different class of service. So something you need to know, Cisco IP phones out of the box are already going to tag their traffic with a priority of 5. So that's voice bearer traffic. So that's the best priority out of the box it can give. Where this 6 and 7, that's reserved for other classifications like kind of control plane traffic. A CoS of 5 is going to be for voice because Cisco IP phones need those quality of service levels that we talked about in the very first video, where it needs to have that one-way latency of less than 150 milliseconds. It needs that jitter to be less than 30 milliseconds one way. So out of the box, Cisco IP phones are going to give themselves a higher priority at layer 2. And then at layer 3, like when this frame eventually reaches your default gateway, it's up to you to have it configured so that we keep this priority on the voice traffic at layer 2. However, when we start to transmit across the wire, then it's important that we actually put our layer 3 marking on that voice traffic to also give it that good quality of service level. So at layer 2, important things you need to know for this, for the CCNA. It's called QoS, class of service. And out of the box, Cisco IP phone has a cost of 5. And we get these costs from these 3 bits in this VLAN header here, which is 16 bits and 3 bits are for that class of service or that user priority. So again, the way it works, right? So let's say this is like through a huge campus network where there's a lot of switches on this link. Then this big boy. Through each switch hop, if we're recognizing that CoS in the 802.1q header, we're going to give this voice traffic priority when we're coming in receiving on this physical interface and transmitting out. And same thing here. Through this switch, we're going to give, because we're switching based off this ASIC hardware here, and these ASICs look at that layer 2 frame. So it's going to give the ability that at the hardware level to give priority to switching these voice frames, okay? All the way up to then our layer 3 device, which now it's up to this layer 3 device to actually mark this voice traffic and classify it appropriately if we got congestion here and we're implementing layer 3 classification and marking. All right, so now let's get into marking at layer 3. And this is going to, I think from teaching in person, trying to explain this as an instructor, clear and concise, is very hard. Having the student be able to just watch a video one time and understand this, even harder. To learn how we mark at layer 3, it's going to take you a couple times. Unless you're a genius savant, or unless you just understand this stuff very easy, it's going to take a few tries. At least it did for me. And if this video doesn't help you and I just confuse you, please feel free to watch other instructors. The great thing about IT is that we do not gatekeep. At least we try not to, at least in my experience. We're not gatekeepers. The knowledge is free for everyone. Kind of that's the spirit of the internet in the first place, right? So, marking at layer 3. So in that IP header, so this is an IP header, right, guys? There's going to be this field here. It's going to be 1 byte. This is going to be the TOS byte, which stands for type of service. This type of service byte is going to have 8 bits. 6 bits are going to be used for what we call the DSCP bits. That is going to be the diff serve code point. So this is how we mark in a differentiated services model using QoS. We have this 8-bit field or 1 byte field. 6 bits are going to be reserved for the DSCP marking, which is going to give us higher, lower priorities of traffic classification. And it's going to give us different drop rates, meaning this traffic's more likely to be dropped, while this traffic is more likely not to be dropped. And we're going to give it different quality of service levels based on these DSCP bits. So we have something called expedited forwarding, which is going to be these 6 bits here equal 46. I just put what looks like 4B. The decimal is going to equal 46. And this expedited forwarding is the highest priority you can get out of DSCP. Then you have assured forwarding, which is going to be multiple different levels. And then we also have CS bits, which stands for class selection. All right, so let's kind of dive into this, because this TOS bit can be pretty complex, and it kind of goes through how QoS came about and the historical value that we need to go over, or the historics of it. Before we move on, this last bullet point, diff serverware routers implement per hop behaviors, which define packet forwarding properties associated with the class of traffic. Fancy way to say, and I probably pulled that from like Cisco's actual definitions online. A fancy way to say, depending on how this DCP bit, it's ranking, right? Or if it's higher or lower, that's how we're going to classify traffic and then choose to queue and police that traffic based on that marking we gave it. Okay, so originally, when we started doing QoS and we had this field in the IP header that we decided we wanted to use for quality of service, what we had was something called IP precedence, where we only gave an IP packet 8 different values, 8 different classes, and we called this the IP precedent field. So in that type of service byte, we still had 8 bits. So 1 or 0, 7, right? That's 8 bits. Well, these first 3 bits is how we classified or marked traffic. And we called that a class selector. So if we had 3 bits here, let's say these 3 bits are binary chart. If we had 0, 1, 1, well, that equals 6, right? So that means if we decided to turn these bits on, this bit and this bit, that means that this IP traffic that we're marking here was going to be in a class selector of 6, which gave us inter-network control, which means essentially that that's a higher priority. This may be like some of that control plane traffic I was talking to you about, stuff we need for the enterprise to work, like DNS, DHCP. Again, what that isn't really a control plane, but our network management protocols like DNS, DHCP. So this was called a class selector. And you can see that we still had 5 bits left over. Now, I can't remember what those 5 bits were for, but in this old TOS byte, this type of service byte, the IP precedence was the only way we were marking traffic within this field, this 1 byte field in the IP4 header. And you can see that gave us 8 different classes of priority to assign to traffic or to classify traffic. But we still had all these bits left. So as QoS evolved and we decided we wanted to maybe classify 11 different types of traffic, and we wanted some more control or ways to decipher which traffic is more likely to be dropped, which one isn't, give different priority levels than just these 8 class selectors, we decided to use the rest of these bits, the next 3 bits. And then that gave us a DSCP bits. But the IP precedent bits never went away. So let me talk about that. So in this DSCP bit, this is the current type of service byte you're going to see. So the newest routers, right, newest ISR routers, they're going to classify traffic based off their DSCP's values. So as you can see here, these first 3 bits, which were just used to do that IP precedence, and those class selectors, right, where we had CS0 through 7, the 8 different classes. Well, we added these 3 bits to create DHCP bits. Well, we got assured forwarding bits in different levels, AF 11, 12, 13, then 21, 22, 23, 31, 32, 33, and then 41, 42, 43. And then the highest level, or the best priority we could give, was EF, expedited forwarding, which was that decimal value of 46. So with DCP bits, these are the only DCP bits we have. And if you do that kind of decimal conversion, these are the conversions, right? So if we actually kind of break down these 6 bits, so now let's put our chart. 1, 2, 4, 8, 16, 32. And let's say we do 1, 0, 0, 1, 1, 0. If we add that up, that's 32 plus 4 plus 2, that is 38. So the decimal value is 38, and the AF value, the assured forwarding value, is AF 43. How do we get this, though? This number 43. Let's take a look. And I'm going to move on to the next slide. And this one, we'll come back to this. But I want to start right here. Okay. So before we go ahead and get started, what I'm going to do here is open up EvenG, because I want to kind of use the CLI to guide us through this as well. All right, that's fine. We just need a router. It's already turned on. Let's go back here. Okay. So if we come back here and look at this chart, we have this chart of DHCP bits, right? Yes, we do. It shows us the DHCP value in binary, what the decimal value is, and then the DHCP meaning here. So if we come back and look at the total 6 bytes, though, the first 3 are still going to be part of that class selector field. And then depending on these next 2 bits is going to determine if it's going to turn into a DCP bit or not. So let's talk about that. You know, what do I mean by that? So let's take a look at the CLI. So I'm in the router here. And remember, right now we're talking about classification and marking. So the way we do this, and this is going ahead of the slides a little bit, to classify traffic, is we create a class map. And then we're going to match this traffic. So we can match IP. And look, we can either put a DCP bit or an IP precedent bit. So even though this is older, the IP precedence and the way we define traffic, we can still use it. So now you may be wondering, well, okay, what if we have a scenario like this where this router understands DHCP and this router just understands IP precedence? Well, then what? Well, you're going to notice something when we get into the binary values. I'm going to cut this off like this. Stop it right here. Okay. When we look at these AF bits, oh, that's going to mess us up. This CDP mismatch. Let me fix this real quick. I believe that should be it. Let's go back to our class map. Test, match, IP, DCP. Match, IP, DHCP. Okay, whew, now let's start over here. So, let's say we have something like this. And through that, guys, I'm not trying to teach you CLI right now, but did you see how many options we had for classification and marking? Yeah, That's why some instructors take, 10 hours to teach QoS because you need it if you want to deep dive. So back to our example here. Man, that is going to mess us up. Let me go ahead and put this video on pause. And then, well, actually, let me just see if I can shut this interface here. Gig 0, right? So I'm telling that into this switch or this router. So that terminal no monitor should have stopped this command from coming up. It's just an evangeism. Yeah, and during the lab, I could explain why this is coming up, but now that it's down, I'm pretty sure we'll be good now. We won't see that error come up. If it comes up one more time, I'll pause this video, and then I'll fix it and come back. All right, let me just expand this a little bit too. Okay, back to our scenario. DCP router talking to an IP precedence router. IPPP or IPP. So I'm going to make those lines again. So we have 4 different, I guess, categories of AF, assured forwarding DCP bits, right? The AF 10s, AF 20s, 30s, and 40s. And then if we come down here to these class selectors, we have CS1, 2, 3, 4, and I'm going to stop right there. Now, what's something we notice about the first 3 bits when we look at AF11 through 13 and class selector 1? What do we notice? They're the same. Remember, in that original TOS byte, only the first 3 were used to make our class selectors. We weren't using the rest of the bits. So that means when you're doing a TOS IP precedence, the next 3 bits were always zeros. But these first 3 bits always had a value in them. So CS1, the first 3 bits were 0, 0, 1. And then the rest were all zeros. Well, now let's take a look at AF11. It's 6 bits entirely to get an AF11 DCP value. What do we notice about the first 3 bits? They're the same as class selector 1. And then we get 0, 1, 0. The next 2 bits are changed. What do we see with AF12? The first 3 bits are the same as class selector 1. And then then the next 2 bits are changed with that 3rd bit being a 0. And when I say that 3rd bit, yes, that's technically the 6th bit, but just talking about the 3 bits after the class selector, right? Like, let me get rid of that because that line may look like a 1, right? So this is like our CS bits. And then these are our AF bits. And then what do you notice about AF13? I know I'm kind of beating a dead horse. The first 3 bits, again, are the same as class selector 1. And then the next 2 bits are changed. Then that 6th bit is again a 0. All right. So why am I doing this? What's the point? Well, when we do DHCP bits and we choose any of these AF values and we send over to an IP precedence router that only speaks IP precedence, it's only looking at those first 3 bits anyways. So if it gets an AF13 bit, it's going to think that is just a CS1 bit or CS1 traffic, even though we gave it AF12. Okay? So yeah, that may mess up our complete topology, but for the most part, there's that backwards compatibility between DSP and IP precedence. But there's not that, I guess, forward compatibility where class selector bits, those first 3 are only those first 3 and that's it. DHCP gives us a lot more options, as you can see here with these assured forwarding bits. Okay, so with that being said, AF 20s, the AF 30s, the AF 40s, they are going to be a part of these different class selectors as far as any IP precedence enabled router is concerned that can't read the DHCP bits. And it's pretty cool. We also get the binary values when we do this question mark command when we go to market. So why don't we have AF 51 or 53? Well, because our DHCP bits, they only go up to 46. And then once you get past 46, these first 3 bits start to change, and DHCP it doesn't do that. It only goes up to 46 as a decimal value. Okay? All right. Because you can see here the last DHCP bit's EF. You can see that this would belong to class selector 5 technically, but that's our last DHCP bit. There is no add-ons. And you may be wondering, this 6th bit, well, it's not being used. Well, technically it is. Because if you notice something about these AF bits, they always are going to end in even numbers. And this has to be 0 for any of these DHCP bits to end up as an even number. So, and some iOSs, you can even just do a decimal value. Like you see this right here. So if I choose 43, is 43 a DHCP bit or a class selector bit? No, it's not. And why is that? Because to have the class, to be a part of IP precedence 1 through 7, your last 3 bits have to be all zeros. Out of those 6, the last 3 have to be all zeros. To be an AF bit, you have to end in an even number. And this 6th bit has to be a 0. If we convert 43, the number 43, into binary, what do we get? So if we put our chart here, because remember, the DHCP bits, that type of service bit, only has 6 bits, and then these last 2 are reserved for something called ECN, which I'll talk about before we move on. What does 43 convert to? Okay, so that's a 1. 43 minus 32 is 11, so 0. 11 minus 8 is 3, that's a 1. 0, 1, 1. That last bit's turned on. So that can't be DHCP. And then these first 3 bits say that it's part of class 5, but then since these are not all zeros, it's not a CS bit. So it's just 43. It's just the DHCP of 43. Or that's it, right? It's not an actual assured forwarding bit. Okay, so now let's go over this a little bit. Let's give some examples. So let's look at this bit. Let's look at these bits. Are these going to be an AF bit, a CS bit, or neither? Let's check it out. So the first 3 bits, they equal 5. Right? So that technically could be a part of class selector 5. However, the next 3 bits aren't zeros. So it ain't a CS bit. However, it could be an AF bit. Because the 6th bit here is a 0, it's an even number. Well, if we convert this to decimal, what is the decimal value? Remember, AF decimals, as if you convert these AF bits to decimals, regular numbers, it ends at 46, right? So AF ends at 46. So it can't go past 46, right? If we convert this, 32 plus 8 is 40. Plus, let's see here. Yeah, 32 plus 8 is 40. 44. Is 44 a DHCP value? It is not. And why is that? Well, because these first 3 bits, they are part of class selector 5. Well, there is no AF bit a part of class selector 5, unfortunately. So even though this decimal value equals 42, that is not an actual AF value. That's just a value of 42. So this binary is neither. And we don't have AF52 because that could be it. We don't have that. So to kind of go forward with these AF bits, they're always going to start with either 0, class selector 0 or 1 through 4, right? So it's always going to be starting out like this. And then these two bits will be changed. So 0, 1, 1, 0, 1, 1. And these are going to be AF11, AF12, and AF13. Right? And then these bits, if it's all zeros after, is CS1. So if you kind of want to do like a top-down overview of this, you have CS1, and then AF11, AF12, and AF13. This is the IP precedence. These are the DSCP assured forwarding bits. And the one thing they all have in common is their first 3 bits are the same. And then we differentiate even more with the AF bits by changing the next 2 binary digits. Whew. Now, okay, I hope that didn't confuse you too much. Do we just have one last thing to go over about marking? And that is the drop probability. So I've explained to you the differences between class selector and AF bits and DCP versus IP precedence. We should have an understanding of that. But now we're going to look at the drop probability. So if we classify traffic as AF11, and then we classify traffic as AF13, what we're saying is that traffic in AF11 is better than traffic AF13 because this has a low drop probability, meaning we don't expect this traffic to drop. Okay? And then as we go down the line, it's kind of opposite. You would expect AF43, yeah, that's, that's better. And you would expect that. But really the best traffic we have is low. And this is kind of weird. It's kind of hard to explain. But essentially what this is saying that if you have traffic that you suspect won't just drop without QoS, you give it this 41. If you expect traffic to drop more than other traffic, you give it AF43. So essentially, if voice traffic would be better off here because it drops a little bit more, and then data traffic would be better off here. Okay, does that kind of, I hope that makes sense. And then really voice traffic should have the EF bits in it. So this just goes over the drop probability, and then this is how we describe it. So AF11 is all priority. And then AF10s, 11 through 13 is priority. AF21 through 23 is immediate. 31 through 33 is flash, meaning immediate, like it's even more immediate than immediate. Do it. And then flash override, meaning this traffic needs to be sent at the highest of priorities. And then EF means critical, essentially saying that, hey, this is critical traffic that needs to happen for our network to stay up or for business to be conducted. Okay, the last thing we're going to go over before we stop this video, because I think I made this video a little long, almost at 35 minutes now, is the trust boundaries. And this just defines where QoS marking is either going to be trusted or not trusted, where it's going to stay or not stay. So like we kind of went over already with these trust boundaries, if this computer is connected to us here, our customer edge, and this is our provider edge router, and they don't want to trust our QoS markings because they got their own thing going on within their own ISP network, and we don't have like an MPLS network where our traffic can kind of seem direct to both our spokes here, our hub to spoke, then our trust boundary is right here essentially, meaning it's not trusted. So who knows if that ISP is going to keep our markings and our classifications of traffic? More likely it's not. So end to end, we need to understand our trust boundaries within our QoS networks. All right, so that's going to cover QoS classification and marking. I hope, it wasn't too confusing, because it definitely can be. And I hope the binary kind of made a little sense and why we went over it. Well, with that being said, I want to thank you for viewing. And then stay tuned. In our next video, we're going to go over queuing.